Right, C3, Jan 2010, the old specification. Question 9, a lot of functions, E's and LNs. So we'll find the exact solutions to those equations. First one, I'll do e to the power of both sides to get rid of the LNs. E to the ln something is just to something. So 3x minus 7 equals e to the 5. Add 7 divided by 3. The next one, if I do the ln's both sides, I'm going to use the log rules here. I've got 3 to the power of x multiplied by e to the 7x plus 2. So when I'm multiplying here, I'll add the ln's. Now, I can simplify this because I can bring the x down. So that's x ln 3. This term is just 7x plus 2, still ln 15. So what I'm going to do, I'm going to take the 2 over and isolate the x's, take the x out as a factor. And now they've got the x's on its own. And divide by that bracket. Last one, what you don't do is ln this plus ln that, because that's wrong. I've got a plus there. It's if it was multiply, I could break it into the logs, but this is add, so I can't just ln everything. What I can do though is multiply it all by e to the x. This will be e to the x all squared. This one will just be 3, and if I take this over, this will become 4 e to the x. That'll be minus 4 e to the x. I've got a quadratic then in e to the x. Which factorizes, some people make that z squared minus 4z plus 3, which is fine. So e to the x is equal to 3, or e to the x equals 1, which means the x is ln 3 or ln 1, and ln 1 is 0. Then we've got some functions, f and g. F is e to the 2 to the x plus 3, g to the x, g of x is ln of x minus 1. Got a domain there of greater than 1. It's got to be greater than 1 because you can't have the ln of a negative. Right, so inverse f minus 1 start off with standard procedure, y equals e to the 2x plus 3. Take the 3 over, I've got to make it say x equals. So do the ln's both sides and then halve it. So and make sure you write f to the minus 1 of x is a half ln of x minus 3 at the end. The domain of f to the minus 1 is the range of the original function. We've got the whole of the e to the x graph, e to the 2x, or e to the x looks like this, e to the 2x looks exactly the same, it's just squeezed towards the y-axis, and then plus 3 moves it up by 3. So the range is going to be greater than 3. You're going to have this at the asymptote there at 3. So that's the domain of f to the minus 1, which is the range of the original function. The composite function, fg, we need to do f of g of x. So we'll do f of ln of x minus 1. So we put ln of x minus 1 in where x is here, e to the 2x. Now they give you the maths for that, but you can simplify a little bit, put the 2 up, and then sort of cancel out the e and ln bit. Because you've got e to the ln something. So now the range of that is greater than 3 because I can't have this being negative because I've got something squared. Then I've added an extra bit. What if the domain of g were greater than or equal to 2 instead of greater than 1? Well, the graph that would look, that's the ln of x minus 1 graph. Is the ln x graph has got an asymptote on the y-axis, but because it's x minus 1, it's been moved to the right by 1. It's going to hit the x-axis at 2. And like I said, it's got that asymptote at x equals 1. And if I say that the domain of g is greater than or equal to 2, I lose all that part of the graph. So it sort of starts there. And the range then of g is going to be greater than or equal to 0. It was the whole of the real numbers because we've got the whole of the ln graph. Now that's going to be the domain of f because the numbers that we get out of g go into f when we do the composite function. And if I draw the graph of f, we've got a range of greater than or equal to 0. Now, originally we had the whole of the graph, all the real numbers, asymptote at 3, hit the y-axis at 4. So the range of g of f originally was greater than 3. Now, because I'm getting rid of all the less than 0 values, the negative values, because the range of g is the domain of f. So I get rid of all those values. It starts at 0. So that's going to be the range of it. If it was greater than or equal to 4. Like I say, it was greater than 3 because I had all these other values in as well. If I think about the simplified version of the composite function, it's quadratic, but we had a restricted domain. The values at G were greater than 1. So we didn't have those values to start off with. It was just this part of the graph for the composite function. And that's where we've got the range there of greater than 3 originally. If I changed it to greater than or equal to 2, so 2's here, I'll lose all those values, and that's where I get the range of FG greater than or equal to 4, just where I had the range of F before was greater than or equal to 4.